So, number 2. Why do you think we would call this a continuous graph? Look at the picture. Why would this be continuous? No breaks, right. There are no breaks like in the other graphs where you actually had to lift up your pencil and then drop it down again. So this one is nice, smooth curve, and if you're thinking about it, I don't have to lift my pencil. To draw the graph, okay? So next year in calculus, you'll hear this term called continuous quite a bit, all right? So you'll have to notice that and work on that, okay? All right. Shh, ladies at the back, okay, and gentlemen, work on your own things, please. I can hear you up here. So let's look at graph number 2. And notice for graph number 2, what do we have about the degrees? The numerator of the degree is 2. The denominator of the degree is also 2, and they're equal. So let's look what happens in this case. And my equation here is y equals to x squared over x squared minus 4. Let me enlarge this a little bit so you can see a little bit better. Okay? My question to you here now is, what is the behavior near your non-permissible value? So first of all, what are my non-permissible values? Positive and negative 2. Good. And we get that from looking at your denominator. Okay. Now, what I'm asking you is, what is the behavior near it? So I'm going to use that limit notation again. What's the limit as x approaches to, let's say, negative 2, first of all. We'll put that one here in blue. And let's approach it from the left. Okay. And then I want you to also figure out what happens when it approaches from the right. Okay. And then I guess we have another one over here, which I'll put in green. So I'm going to ask you also, what's the limit as x approaches to positive 2 from the left? And also the limit as x approaches to positive 2 from the right. Okay? And we're going to use this calculus notation now to help us describe this behavior. Okay? Near. And notice I use the word near. Not equal to, but near these asymptotes. And can someone suggest to me what we get for the first one here? The limit as x approaches to 2 from the left. That means I'm traveling along the curve from the left. And where does it go? Up, 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 and away to something we call infinity. Good. And what happens at x approaches to negative 2 from the right? It goes way, way, way down to negative infinity. Okay? How do I draw the infinity sign properly? I start like this in the loop, and I go around, come around, like that. Like one of those racetracks you used to build when you were young. Okay? Okay. Okay, ladies and gentlemen, what about the next asymptote here? The one that's in green. 2 from the left. What's the value? Way down here. Negative infinity. 2 to the right. Positive infinity. Now, once again, Mean Girls. Mean Girls alert. Okay, remember that movie Mean Girls? When they said, what is the limit at the actual value? Well, if the limit from the left goes up here and the right is down there, then what's the limit at that value? In this case, the limit at x approach to negative 2, the actual value of negative 2 is, what did they say in Mean Girls? Does not exist. D-N-E. Does not exist. For those of you who watched that movie. I heard that Mean Girls was actually on TV last weekend. Channel 19. Channel 19?
I don't know, they always show that one.
I don't watch Channel 19. That's the Women's Network. Okay. Now, ladies and gentlemen, question number 2 for this one says the following. Notice it says, what is the end behavior of this function look like? End behavior meaning, tell me what happens in this scenario when the limit as x approached to infinity. What's that equal to? And tell me what happens when x approaches to negative infinity. So now I'm talking about the x values. Really far to the right, really far to the left. What happens? Okay, so ladies and gentlemen, at infinity, that means I'm over here, and someone said it approaches to 2. Please do not make a common mistake my grade 8s do. What is the scale on this graph? Every 1 square is equal to half a unit. So this is not 2, but it's actually 1. So notice that the limit as x approaches to infinity, meaning what happens when you are way, way out here to the right, the y value gets closer and closer to, looks like it's 1. And then what happens over here, going this way? It also equals to 1. Now, do you see how I drew a dotted line going across? Didn't I draw a dotted line going up and down to represent a vertical asymptote? So what do you think this thing is? Yeah, this is a horizontal asymptote. And it's at, the equation is y equals to 1. So notice we don't just have vertical asymptotes, we could also have horizontal ones. And if you weren't scared enough, if you look at graph number 3, we have another type of asymptote. Diagonal ones. Which we don't call diagonal ones, but we'll call something else. And I'll show you that right now. You're actually right. Okay, dear friends, number 3. Okay, things get trippy right now in 3 and 4. Okay, number 3. Notice what I have in number 3. The degree of the numerator, okay, x squared, is 1 more than the degree of the denominator, which is just x. Now, question to you here again. Not why happens, what happens? Okay? So, what happens to y when x is very close to 5? Let me ask you to find this for me then. What's the limit as x approaches to 5 from the left? Okay, and I also want you to find what's the limit as x approaches to 5 from the right. Okay? So go ahead and figure this one out, please, on your own. Okay, so what's the y value when it's from 5 to the left? So here's 5, my vertical asymptote. From the left, I'm traveling along here, and it goes... where does it go? Where does it go? Down to negative infinity. Okay. And what happens when you're going 5 to the right? So now the graph is up here. What happens when going 5 to the right? It goes all the way up to infinity. Okay? And once again, when I have the limits from the left and the right not equaling each other, the limit at 5 is something that we call does not exist. Okay? Now, my next question to you in part 2 is, what is the end behavior of this function? So once again, I want you to tell me what happens when the limit as x goes to infinity, and I also want you to tell me what happens when you have the limit as x approaches to negative infinity. So tell me once again, when you go far to the right and far to the left, what's my y value for this particular example? So for the one to the right, I'm over here, and look what happens. Does it get closer and closer to a number? Or does it look like it's curving upwards and going up forever and ever and ever? Up, yep, up, up, up. So you go forever and ever, up, 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 up. What do we call that? Infinity. Thank you, Betty. Infinity and beyond. Okay, good. Infinity. Now, what about negative infinity? Way over here. Negative infinity and beyond. Good. So notice in this case here, we still have graphs that go up to infinity and down to infinity. I guess there's no horizontal asymptote. But, like what Gavrilo mentioned earlier, we do have this diagonal asymptote, which I'll mention in a moment. Okay? So I'll say here, you do have some sort of what I call diagonal asymptote. Okay? Okay, ladies and gentlemen, the last one is the most important. Okay? The one that I feel like you really need to know. It is easy. Good, thanks. This is the one where there is a common factor between the numerator and the denominator. Okay? Here's my function, y equals x squared minus 9 all over x minus 3. And the question here is, why does the graph look like a straight line? And how would you support your response by using algebra to help you out? Yes, Megan. Okay, so ladies and gentlemen, remember how we did chapter 6, rational functions? I asked you to simplify this. How would you simplify the numerator? That's right. You factor x plus 3, x minus 3, all over x minus 3. Cancel. So what do you have left over? X plus 3. Now, from grade 10, I hope you remember that y equals to x plus 3 is a straight line. So really what you've told me is that this rational expression is equal to this straight line. Almost. Wait, there's more. Megan said, look, Mr. Lee, there's this open dot here. Why is there an open dot at this particular value? NPV. So why, or what does the open dot in the picture represent? Remember, notice here you have an NPV, a not permissible value of 3. So this open dot here represents your NPV. Okay? Now, the reason why we use an open dot is it would look weird if I draw an asymptote, because the graph actually doesn't get closer and closer to the asymptote. It's a straight line. So therefore, to show that nothing exists at 3, we just draw in an open dot. And by the way, this value here is 3. Okay? Okay? All right. Ladies and gentlemen, we've talked about these asymptotes. I'm going to show you how you can calculate them now. Okay? So turn to page 3 and I'll show you how you can calculate these asymptotes. And that's a big part of calculus as well. All right?
Oh.
Oops. 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 Oops.